What is a generalized eigenvector eigenspace? I think that several of you has never heard about the term generalized eigenvector eigenspace. Let's make a summary of where we are. We have that whenever we have an eigenvalue, the eigenvalue is essentially determined by the fact that kernel of lambda I minus a is not going to be a trivial kernel, true, for this modified matrix. And in a certain sense, this one is going to be a subspace, and this one is going to contain some eigenvectors. Together on this up to now, 1, 2, 3? Perfect. We also saw that sometimes it happens, for example, for a matrix like 3, 1, 3, 0, this one, we can always find some eigenvectors, but we are not able to find a sufficient number of independent eigenvectors to form a basis. We will see that while eigenvectors will not in general form a basis, whenever we complement eigenvectors with generalized eigenvectors in eigenspaces, we are going to be able to form a basis. Okay? Okay, so we are going to go basically adding some possibility. Why? Because we saw that eigenvectors by themselves in general do not guarantee us to represent the whole space. How much are we aligned in terms of what we are going to do right now? 1, 2, 3. And the need for this. We need it because we want to have a basis. Perfect. So, we saw yesterday, I think, those two cases where we were having that if we take lambda for A1, lambda for A2, in both cases, lambda is an eigenvalue. In this case, this was the eigenspace associated to lambda. In this case, this was the eigenspace associated to lambda. Do we remember this, 1, 2, 3? We have to be together. How do we find this object here? Basically, we write 0, 0, lambda minus beta. This is the modified A. And we try to find the kernel of this stuff here. The kernel of 0, 1, 0, 0, 0, 0, 0, 0, lambda minus beta is essentially spanned by that vector. If instead we write 0, 0, lambda minus beta, this matrix here has a kernel, that is this stuff here, and that is the eigenspace. Geometric multiplicity of lambda for A1, dimension of this kernel here, 1. Geometric multiplicity of lambda for A2, dimension of this space here, 2. Okay? Perfect. Now, very interesting. This stuff here has dimension 2. If we find kernel beta I minus A2, this is going to be bet. What is it going to be? This is going to be beta minus lambda 0. This is going to be 0, 0, 1 together. Can we form a basis of eigenvectors for R3? Yes. 1, 2, 3. True? Can we do the same for A1? Well, this one is going to be also the eigenspace of beta for A1. Do you see it? Think 30 seconds. That same kernel of beta I minus A2, we can also write it as minus A1, and it's going to be the same vector. Tell me if we agree with this. 1, 2, 3. Think 15 seconds, and let me know if we agree on this. The eigenspace associated to beta, both for A1 and A2, is 0, 0, 1 in the span. How much are we together, people? I see several people not together, so we do some visualizations. If I take A1 and I represent it with the A columns, we are going to have, so x1, x2, x3, and then we're going to have, I think, so we have alpha 1, alpha, beta, or lambda, let's say. Let's pretend that lambda is 0.5, okay? So the first column, A1, is this one. A2 lies here in the x1, x2 plane. A3 lies here. Are we together? Do you see it? 1, 2, 3? Perfect. If I was representing A2, this one would be this one. Together? Are we together on this? Perfect. Let's go back to A1. It's block diagonal. It means that essentially there's two components that are independent. True? There's the evolution on this space, x1, x2, and the evolution on the x3 space. True? Along the x3 space, this is going to be an eigenspace, because if I start here, what do I get? I get something that aligns with A3. True? Do you see it? If instead I start in A1, or better, x1, if I do times 3, 0, 0, what do I get? Do I get something on this space or something on this line? On the space 1, on the line 2, you do not know 3. Discuss. What would you say, people? On the line, because whenever I take this point here has got a coordinate x1 different from 0, coordinate x2 equal to 0, coordinate x3 equal to 0. Together? Perfect. It means that whenever I go see stuff here, I take this amount of time, what? A1. True? That means that I stay on x1. Together? If I was having something here, I would take a combination of A1 and A2, and I would stay on the plane. How much are we together? Perfect. So, going back. This matrix, I see immediately one eigenspace and another eigenspace. This matrix here, I see one eigenspace, another eigenspace, another eigenspace, because they are all independent. Are we together? You put it immediately. If you put 7, 0, 0, this stuff here will give you something that is number 0, 0. True? And you see? V lambda V. Together? Perfect. Yeah?
When we have columns that are linearly independent, we can already say that no.
No, definitely not.
Okay.
Definitely not. Is that I see that I've got an upper triangular.
Okay.
I've got an upper triangular, and actually I've got an upper block triangular. Anyway, are we together that if I put 2, 3, 0, this stuff here, I do not get something that is going to be alpha 2, 3, 0. Are we together that this is going to be different from this? True? Perfect. So this one is not in the eigenspace. Essentially, this one is the eigenspace of lambda for A1. 0, 0, 1 will be the eigenspace for this and this. Together? Perfect. How many linearly independent eigenvectors can we take for A1? 2. 1 and 2. How many can we take for A2? 3. 1, 2, 3. Together? do we see that here in this case we are missing one dimension? We are missing one dimension, true? Are we together on this? 1, 2, 3. Without those things here have to be extremely clear, okay? So if you see that the mechanisms are not there, you've got to put efforts in understanding them. Are we together? Perfect. Now, in this case, we are missing. In this case, not. What is missing here? We have a geometric multiplicity for lambda that is 1, but we have a block that is 2. So it's lambda that is the problematic one that is missing something. I see perplexed faces. Are we together that here we cannot find a basis of eigenvectors? Are we together that to beta, how many, the subsystem formed by beta, which dimension does it have? 1, true? The subsystem formed by beta, does it have one eigenvector that is linearly independent from the other eigenvectors Absolutely yes. Lambda, the subsystem formed by lambda, what dimension is it? 2. How many eigenvectors that are linearly independent can I find in lambda? 1. Do you see that lambda is missing something, people? Perfect. Here, dimension of the lambda block, 2. How many eigenvectors can I find here that are linearly independent? 2. Here, lambda is not missing anything. Are we together, people? Perfect. Let's focus on this. Is missing one dimension. Let's take a power. Let's take the kernel of the modified matrix to the power of 2. So we have this one. Then we take lambda I minus a square. What is it going to be? This one is 0, 1, 0, lambda minus beta. True? It's something that looks like. This one is going to be something looking like 0, 1, 0, 0, 0, 0, 0, 0 number. True? To the power of 2. This is going to be equal to, you compute it. It's the trick of yesterday. We have 0, 1, 0, 0, 2. And we are doing to the power of 2. In that case, what do we do to the ones? We move them. True? We are going to get something that is 0, 0, 0, 0, number squared. That I don't care too much, though. And now I'm telling you that we take the kernel of this stuff here, and it's the kernel of this stuff here. Let's see if you see it. To find the eigenvectors, what do? We do not consider this one. We consider 0, 1, 0, 0, beta, or better, number. True? And then we were trying to find the eigenspace associated to lambda was essentially given by the first column. True? True? And now I'm telling you, now we take this stuff here and we do to the square, to the power of 2, and we get this one. True? And we take the kernel. And the kernel is going to be both. True? You see it? Are we together? Do you see that I am actually, if I consider this kind of chain of kernels, I was dimension 1 here, and here I can add the dimension that was missing. Do you see that by doing this operation of powering up, I'm getting something that is kind of missing before? Do you see it? Are we together that whenever we take this one and the lambda subblock, and the lambda subblock was having this one only, or better, 1, 0, 0 as eigenvector. True? Now, what do? We take this power, we get this stuff here. This one is in the kernel of this. Now, by looking at the kernel of this one, we have also this vector here that is the one that was missing to form a basis. Because we want to have a basis. Eventually, we want to have a basis because you will see By forming a basis, we are going to be able to express this t to the power of m, etc., etc., etc. Okay, so that's why I'm stressing the we need the basis, because the basis will be connected to those t to the power of m. We didn't do discrete system, so this slide here maybe it's not going to be very now that I think not meaningful. Let's make an example. Geometric multiplicity associated to lambda for this case. You should see it immediately. Geometric multiplicity associated to this is the dimension of the kernel of lambda minus a. True? Subsystem. How many lambdas do I see? 3. How many blocks do I see? 2. This block here will associate the eigenvalue eigenvector this. This block here will associate to the eigenvector this. Do you see it? This 0, 1, 0, 0, that goes hitting this column. You see that I'm hitting this column. If I do this operation, what do I get? 1 lambda 0, 0. Is it aligned? No. You see? Whenever I've got a structure that looks like this one, the initial part, the first topmost part, is the one that is associated to the eigenvectors. I see it, kind of, I don't know, I don't see it. Let's make an example and then you do it. 3, 1, 3, 1, 3, 3, 1, 3, 3, 3, 9, 9, 1. Geometric multiplicity associated to 3. Go, discuss. Find it and discuss. People, what would you say? 4, true? Why 4? Because I've got one block, another block, another block, another block, and another block. But it's a 9, so I don't care. Eigenvector associated to this first block is going to be this one and all zeros. True? Is this one going to be an eigenvector? No, because I go touching this low line here. If I do this operation, I will get 1, 3, 0, etc. True? This one, is it going to be an eigenvector? You do it. No, because what do I get? What do I get? I get 1, 3, 0, 0, and all zeros. True? And they are not. You see that they are not aligned. Are we together? If instead I take 0, 0, 0, 1, 0, and all zeros, what do I go hitting? I go hitting this one. True? Do you see it? What do I get? I get 0, 0, 0, 3, 0, and all zeros. Eigenvector. If I take this one, do I get an eigenvector? No. So how many eigenvectors do I get? 1, 2, 3, 4. You see them? So if I take, let's ignore the 9s for now. For about 3. Let's see if we focus on 3, we get 4. And if I take the eigenspace associated to 3, the eigenspace is going to be formed by 1, 0, 0, 0, 0, 0, etc. 0, 0, 0, 1, 0, 0, etc. 0, 0, 0, Let me think. That I've got to be careful to do not make a mess. No, this and these zeros. Are we together? That is my eigenspace associated to the eigenvalue 3. Together? Perfect. Am I missing something if I want to form a basis? Of course I'm going to miss something, because here I got something that has dimension 7. 7, yeah. So by the way, geometric multiplicity, here, geometric multiplicity of 3 is going to be 4. Multiplicity in the minimal polynomial associated to 3, discuss. It was the power, the biggest power that I need to go lambda minus a, lambda I minus I, go to 0. No, power of 3.
Four. The thing that you shift to obtain the zero. So 1 1. We focus on the first block.
Let's see the others what they say. So 5 means you do not know the other numbers. Means that you computed. I would like everybody to answer, people. This is very important for me to understand where we are. Okay. The multiplicity in the minimal polynomial, I've got to do what? I've got to take lambda I minus a. In this case, 3i minus a. It means that I'm getting 0, 0, 0, 0, 0, 0, 0. And then I've got all the blocks, true? And I've got to raise the powers until I get only zeros. Okay? Are we together on this? It's essentially driven by the biggest of those mini blocks. Which power do I need to throw the zeros, the ones out? If I do to the power of 1 is this one. To the power of 2 is going to be this one. True? Power of 3, I'm going to throw everything away. Okay? So multiplicity in the minimal polynomial for 3 is going to be equal to 3. Okay? Let's make an exercise. If I was having this one, okay, do you see the situation? Geometric multiplicity of 3, multiplicity in the minimal polynomial of 3. Go, you tell me. Discuss, people. So the top one is going to be the geometric multiplicity. No, it's the number of blocks, so it's 3. One eigenvector, another eigenvector, another eigenvector. Okay, perfect. Multiplicity in the minimal polynomial is driven by the biggest block, 5. True? Perfect. Algebraic multiplicity of 3 is how many 3's you see? 7. Together? Perfect. Just to finalize, if I tell you G and I tell you M, but I don't tell you where I put the numbers, or better, if I tell you algebraic and I tell you geometric, okay? I tell you the algebraic multiplicity and the geometric multiplicity, okay? Can you determine the multiplicity in the minimal polynomial? Discuss. Is the question clear? I give you two numbers, and I don't tell you where the ones are. I tell you that there's this one is 7 and this one is 3. Can you determine them? Go. For this specific case, go. Think in the way you think that I think too. It's kind of a little bit tricky. So let me know. I can determine, I cannot determine, I do not know how to answer. And I see several tools. Perfect, excellent. Because if I have those ones like these ones, I have one block, one block, one block. I've got geometric multiplicity 3. True? Multiplicity in the minimal polynomial in this case, 3. True? The biggest block, mini block, is 3. True? But if I do this one, still geometric multiplicity 3. Multiplicity in the minimal polynomial, in this case, though, 5. How much are we together, people? Excellent. So another message, geometric in the minimal polynomial and algebraic multiplicities do not give us all the configuration. We need something more that is connected to the length of the generalized eigenspaces chains that we are doing right now. Okay, so multiplicities up to now, we got the point. They do not provide the full picture, but they give us some information. Together? Perfect. Let's go back to this stuff here. At this point, geometric multiplicity of lambda, 2. 2. Algebraic multiplicity, 3. Multiplicity in the minimal polynomial, 2. Together? Perfect. How many, if I consider also beta, how many linearly independent eigenvectors will I be able to find? 1, 2, 3. I'm missing one, I cannot form a basis. Okay? Now, if I do lambda I minus a square, what do I get? I get 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, number 0, 0, 0. True? And if I look at the kernel of the stuff here, in a certain sense, I go checking the stuff that I was missing before. Do you see the mechanism? By raising the powers of the modified matrix, I go checking out, kind of exploring more stuff. Okay? Watch out though. If I was having this situation here, okay, look at this situation here. Geometric multiplicity of lambda, 1. True? Are we together that in this case the geometric multiplicity of lambda is 1? Perfect. How many eigenvectors associated to lambda can I find at the first step? 1. If I do lambda a minus, so lambda I minus a to the power of 2, and I look at the kernel, how many eigenvectors, they are going to be generalized eigenvectors, how many elements can I add? If I do this stuff, I'm going to get 0, 0, 1, 0, 0, 0, 0, 0, 0 number. Do you see it? Do you see that if I do this stuff here for this one that has got this block that is 3-dimensional, I don't get everything 0, true? And I will get only this that I can add. Will I have enough elements to form a basis? No, because I will have 1 and 2 from the original matrix. With the power of 2, I'm adding 1, true? Guess what? What will I need to do? I will need to consider also this one, and at this point I will get this one, true, and I will add also the third one. You see? Together? Let's go back here then, at this point. In this case here, if I want to have this kind of adding elements to my receipt to be able to construct a basis of my space, I will need to do 3i minus a up to a certain specific power. Which power? 5. And 5 in this case is the multiplicity in the minimal polynomial. Multiplicity in the minimal polynomial is going to give us, in a certain sense, the powers that we need to do for doing kernel stuff and to find elements that we are going to be able to find for the basis. How much are we together, people? 1, 2, 3. Definition. Generalized eigenvector of order k relative to the eigenvalues lambda. Lambda prime here, but it's lambda. I did the notation. A vector that is in this kernel, but it's not in the previous kernels, is called a generalized eigenvector. So lambda, so 3, 1, 3, 1, 3, 9. 1, 0, 0, 0 is the eigenvector, true? And it's also a generalized eigenvector of order 1 relative to 3. Together? Then, if I take 0, 0, 0 number, 9 minus 3, and then I do to the power of 2, I get this one. True? And then I look at the kernel of this stuff here, and I get this one, that is this object. True? This object is in this kernel here. True? And here is 3. Are we together? Are we together? And it's not in this one. Read the slide. You see? 0, 1, 0, 0 is not in the iteration 1. True? It's only in the iteration 2. This one, how do we call it? Generalized eigenvector of order 2 relative to the eigenvalue 3. Very much together, not at all, kind of. Tell me how this one, what is the name of this one? Might be also Mario, but it has got also another name in this course. Discuss? Tell me which name it has. How would you call it? During the exam, how would you call it? Whenever we start all the values of the eigenvectors of in the eigenchains, we basically have a number of eigenvectors or generalized eigenvectors that is going to be equal to the algebraic. So, how would you call it? How would you call it, people? Somebody wants to call it? Unit vector. Why would you call it unit vector? I would call it generalized eigenvector of order 3 relative to the eigenvalue 3. Because this one, I need this power here, 3, to get this one. True? Are we together on this? And this one was not in the kernel of this one, that is this one. True? Are we together? Hmm? And this one should, at this point, from a geometrical perspective, I hope this is clear. I have this, and then it might become this, and then it might become this, and you've got kind of that this one might be bigger than this, and this one might be bigger than this, but at a certain point, whenever I hit the multiplicity in the minimal polynomial, the kernels, those chain of kernels doesn't expand anymore. Think at this one. Lambda 1, lambda 1, lambda. This one is going to be given by what? 1, 0, 0. This one is going to be given by what? 1, 0, 0, 0, 1, 0. True? The one, if I put 3 here, this one is going to be given by 1, 0, 0, 0, 1, 0, 0, 0, 1. Do you see it? I see it. I don't see it at all. Kind of see it. This one is 0, 1, 0, 0, 0, 1, 0, 0, 0. This one as a matrix. This matrix here is going to be, this matrix here is going to be given by, if I take the kernel of the stuff here, the kernel of the stuff here, let's make it in red, is going to be given by the span of 1, 0, 0. If I take the kernel of the stuff here, it's going to be given by 1, 0, 0, 0, 1, 0. True? Eigenvector, generalized eigenvector of order 2. This one, which kernel will it have? It will have as a kernel 1, 0, 0, 0, 1, 0, 0, 0, 1. This one is not here and not here. Which name does this one have? Generalized eigenvector of order 3 associated to lambda as an eigenvalue. Okay? But do you see that at this point, if I do to the power of 4, this one to the power of 4, I don't go up. I don't go up. I stabilize the chain. It's called that chain. They are generalized eigenvectors chains. See? Tell me, given this example, if you can find a generalized eigenspace of order 4. A generalized eigenvector of order 4. I can find it, cannot find it, I don't know if I can find it or not. Discuss.
You won't have any other addition in generalized eigenvector, so maximum is 3, or you can. Yeah. So no more for.
So, people, what would you say? Everybody answers, please. The multiplicity in the minimal polynomial here is 3. True? Because it's the biggest block that we are having right now. True? It means that if we look at this chain of things of these kernels, it will stabilize at 3, not at 4. True?
But this is 4 equal to 3. So if you do 4, you get the same.
No. Think at lambda I minus a. If I take lambda I minus a, I've got this one. True? Which power do you need here to get all zeros?
3.
3.
But if you do it 4 times, it's also all zeros.
Yeah, but you do not get something more.
Yeah.
The question was, maybe the question was unclear. Can I find a generalized eigenvector of order 4? No, because I can get only generalized eigenvectors of order 3 at maximum, because at 4 I already kind of exhausted all the dimensions that I want to explore. True? Perfect. At this point, if this is clear, you tell me, find a generalized eigenvector associated to the eigenvalue 3 of order 3. There's only one. I want you to find the generalized eigenvector of order 3 associated to the eigenvalue. Is the question clear? The eigenvalue is 2. Are we together that the eigenvalue is 2? Are we together that the multiplicity, the minimal polynomial associated to 2 is 3? Are we together that we have to find at this point at least one generalized eigenvector of order 3 associated to 2? Perfect. Find it. And you should see it immediately. How many of you see it? So let's do it from a geometrical perspective. What are gonna be the eigenvectors at step 1? They're gonna be this one, and this one, in the sense 1 0 0 0 0 0 0 1 0 0 0 0 0 0 1 0 0 0. True. This one hits this column, this one hits this column, this one hits this column. How much are we together, people? 1 2 3. Which columns will give us the generalized eigenvectors of order 2? This column and this column. Do you see it? So 0 0 1 0 0 0 is going to be essentially in this object, but not in this object. True? Are you following me, people? This one, the same. It's another one. It's this one. Okay? And the unique one that is going to be of order 3 is going to be this one. You see it? Together? Are we together? Let's go back here then. Tell me a generalized eigenvector of order 4 associated to 3. Go, discuss. Generalized eigenvector of order 4 associated to 3. The I minus A gives us 0, 0, 0, 0, 0, 0, 0, something that I don't care. True? So I'm focusing on 3. If I do this to the power 2, what do I get? 0, 1, 0, 1, 0, 1, 0, and those ones zeros. True? For this stuff here, 0, let me find it. 0, 1. No. No, I'm confusing you. Because now at this, so if I do this one, I was having the first column, and that was an eigenvector, true? And also this column were eigenvectors. Whenever I do this, that it means this, I'm adding this one, true? Perfect. If I do to the power of 4, what do I get? I should get this one. Tell me if I'm correct. No, this one, yeah, this one. So I'm adding this one, you see? So the generalized eigenvector of order 4 associated to 3 is going to be 0, 0, 0, 1, 0, 0, etc. Zeros. Do you see it? Hmm? How much are we together, people? I know it's kind of this is important. Read this stuff here. Those are called Jordan mini blocks. This is called Jordan block. Mini block, block. Okay? Read this stuff and tell me if we are together. 1, 2, 3. Jordan block is the whole stuff associated to the vector, to the eigenvalue. This means this kind of I was trying to do something connecting to discrete time systems, but I think I failed because we need more time. So I will change those slides. Is how many generalized eigenvectors can I find? Or better, which order? Which is what is the maximum order that I can find? I'm gonna edit the slides, people. Don't worry. How much do we feel together? It's non-trivial. This stuff is not trivial. I know that this stuff is not trivial. No, too early.
Can you please go through once more the example? Yes,
This one. Okay.
And
so
when you do the step, what is the generalized eigenvalue that eigenvector that we have?
So whenever we are considering this object here, we are considering this object, true? And then we are considering this object here, sorry, kernel. And what we are considering essentially is a 1, 0, 0 as the first, true? Then whenever I do 2, I'm considering this one, true? And in a certain sense, if I look at this kernel here, I have this object. You see it? This object here is in this one, but it's not in power of 1. True? This one is not in the eigenspace. Together? Are we together, people? Perfect. In a certain sense, this one is an addition, and this is a generalized eigenspace eigenvector of order 2 associated to that eigenvalue.
That's why 0, 1, 0, 0, 0. I would have to draw the kernel to see what am I adding.
Do you see that the kernel here you've got 2 columns of zeros?
Yeah.
And the kernel is formed by those 2. True? The kernel is formed by those 2, but you are adding dimensions. You're forming a basis. True? You're not going to retake this one. You already took it before. every time that you go higher, higher, and higher until you reach the multiplicity in the minimal polynomial, is like kind of adding directions. Okay? Okay, people? Let's take a pause.